decades, silicon has been the backbone of computing technology. From the earliest microprocessors to today's powerful smartphones and laptops, silicon chips have driven innovation and shaped our digital world. However, as we push the boundaries of performance and efficiency, silicon is reaching its physical and practical limits. Engineers and scientists are now exploring new materials and architectures to overcome these challenges. This scene sets the stage for our journey beyond silicon, where we'll discover how photonics, quantum chips, and neuromorphic computing are redefining what's possible in the world of technology. Silicon chips become smaller and more powerful. They face increasing challenges. Heat generation, energy consumption, and quantum effects are making it harder to continue shrinking transistors. Moore's law, which predicted the doubling of transistors every 2 years, is slowing down. This has prompted researchers to look for alternatives that can deliver higher performance and efficiency. In this scene, we'll explore the reasons why silicon is no longer enough for the next generation of computing and why new approaches are urgently needed. Photonics is an exciting field that uses light rather than electricity to transmit information. By harnessing photons, photonic chips can achieve much faster data transfer rates and lower energy consumption compared to traditional silicon chips. This technology is already making waves in data centers and high-speed communication networks. In this scene, we'll dive into the basics of photonics and see how it's poised to revolutionize computing by overcoming some of silicon's biggest limitations. Photonics chips are already being deployed in real-world applications. For example, they enable ultra-fast communication between servers in data centers, supporting the massive data demands of cloud computing and streaming services. Photonics also plays a crucial role in fiber optic networks, which form the backbone of global internet infrastructure. By replacing electrical signals with light, these systems can transmit information over longer distances with minimal loss and interference. This scene highlights how photonics is transforming the way we connect and communicate. Quantum chips represent a radical departure from traditional computing. Instead of using bits that are either 0 or 1, quantum chips use qubits, which can be both at the same time thanks to quantum superposition. This allows quantum computers to solve certain problems much faster than classical computers. Quantum chips are still in the early stages of development, but their potential is enormous, especially for tasks like cryptography, optimization, and simulation. In this scene, we'll break down what makes quantum chips unique and why they're so promising. Quantum computers can tackle problems that are impossible for classical machines. For example, they can factor large numbers quickly, which is vital for cryptography. They can also simulate molecules and materials at the quantum level, helping scientists design new drugs and materials. While quantum chips are still experimental, companies and governments are investing heavily in this technology. This scene explores the real-world impact and future potential of quantum computing. Despite their promise, quantum chips face significant hurdles. Maintaining quantum states requires extremely low temperatures and precise control, making quantum computers expensive and difficult to build. Error correction is another major challenge, as quantum bits are sensitive to interference. Researchers are working on new materials and designs to make quantum chips more practical. This scene discusses the obstacles that must be overcome before quantum computing can become mainstream. Neuromorphic computing is inspired by the human brain. Instead of traditional circuits, neuromorphic chips use networks of artificial neurons to process information. This approach allows for highly efficient and adaptive computing, especially for tasks like pattern recognition and learning. Neuromorphic chips can handle complex sensory data, such as images and sounds, with much lower power consumption than conventional chips. In this scene, we'll introduce the concept of neuromorphic computing and its potential to change the way machines learn and interact. Neuromorphic chips mimic the structure and function of the human brain. They excel at tasks that require learning, adaptation, and pattern recognition, such as speech and image processing. These chips are already being used in experimental robots and smart devices, enabling them to respond to their environment in real time. By processing information in parallel and adapting to new situations, neuromorphic chips offer a glimpse into the future of intelligent machines. This scene explores how brain-inspired computing is reshaping technology. One of the biggest advantages of neuromorphic chips is their energy efficiency. By processing information in ways similar to the brain, these chips use far less power than traditional silicon chips. This makes them ideal for battery-powered devices and applications where energy consumption is critical. As we move toward a more connected world, energy-efficient computing will become increasingly important. This scene highlights how neuromorphic chips are paving the way for sustainable technology. Photonics offers several advantages over silicon, including faster data transfer and lower energy consumption. However, integrating photonic chips with existing silicon technology is a complex challenge. Researchers are developing hybrid systems that combine the best of both worlds. This scene compares photonics and silicon, highlighting the strengths and weaknesses of each approach and the ongoing efforts to bridge the gap. Quantum chips and classical silicon chips operate on fundamentally different principles. While classical chips use binary logic, quantum chips leverage superposition and entanglement. This allows quantum computers to solve certain problems exponentially faster. However, classical chips remain more practical for everyday tasks. This scene explores the differences between quantum and classical computing and where each excels. Neuromorphic chips differ from traditional silicon chips in their architecture and function. While traditional chips follow strict logic and sequential processing, neuromorphic chips process information in parallel and adapt to new inputs. This makes them ideal for tasks like learning and sensory processing. In this scene, we'll compare neuromorphic and traditional chips, highlighting their unique strengths and application. Overcome the limitations of each technology, researchers are developing hybrid chips that combine silicon, photonics, quantum, and neuromorphic elements. These designs aim to maximize performance, efficiency, and adaptability. Hybrid chips could power everything from supercomputers to smart devices, offering new possibilities for innovation. This scene introduces the concept of hybrid chip design and its potential impact on the future of computing. Photonics is already making a difference in fields like telecommunications, medical imaging, and high-speed computing. Fiber optic communication relies on photonic technology to deliver fast, reliable internet. Medical devices use photonics for precise imaging and diagnostics. In computing, photonic chips enable faster data transfer and processing. This scene highlights the diverse applications of photonics and its growing influence. Quantum chips are poised to revolutionize fields like cryptography, material science, and artificial intelligence. They can solve complex optimization problems, simulate quantum systems, and break encryption codes. Governments and companies are racing to develop practical quantum computers for these applications. This scene explores how quantum chips could transform industries and drive new breakthroughs. Neuromorphic chips are being used in robotics, smart sensors, and adaptive devices. They excel at processing sensory data such as vision and sound and can learn from experience. This makes them ideal for autonomous systems and intelligent devices. As neuromorphic technology advances, we'll see more machines that can adapt and learn in real time. This scene showcases the practical uses of neuromorphic chips. Race to develop new chip technologies is intense. Universities, companies, and governments are investing in research to push the boundaries of photonics, quantum, and neuromorphic computing. Collaboration between disciplines is key, as breakthroughs often require expertise in physics, engineering, and computer science. This scene explores the global effort to advance chip technology and the importance of innovation. Major technology companies are leading the charge in developing next-generation chips. Firms like IBM, Google, Intel, and startups are investing in photonics, quantum, and neuromorphic research. These companies are building prototypes, launching pilot projects, and partnering with academic institutions. This scene highlights the role of industry leaders in shaping the future of computing. Governments around the world are supporting research into advanced chip technologies. Funding, policy support, and international collaboration are helping accelerate innovation. National labs and research centers are working on quantum computing, photonics, and neuromorphic projects. This scene explores how government initiatives are driving progress and ensuring global competitiveness. As new chip technologies emerge, education and training are crucial. Universities are launching programs in quantum computing, photonics, and neuromorphic engineering. Students and professionals need to learn new skills to work with these advanced systems. This scene discusses the importance of education in preparing the next generation of innovators. Future of computing is full of possibilities. As photonics, quantum chips, and neuromorphic computing mature, we'll see new applications and breakthroughs. From smarter devices to faster networks and revolutionary scientific discoveries, these technologies will reshape our world. This scene looks ahead to the exciting potential of next-generation chips. Advanced chip technologies raise important ethical questions. Quantum computing could break current encryption, impacting privacy and security. Neuromorphic chips may lead to more autonomous machines, raising concerns about control and responsibility. As we develop these technologies, it's vital to consider their social and ethical impacts. This scene discusses the importance of responsible innovation. Environmental impact of chip manufacturing is a growing concern. Photonics and neuromorphic chips offer energy-efficient alternatives, but quantum computers require significant resources. Researchers are working to minimize waste and energy use in chip production. This scene explores how new technologies can help create a more sustainable future. International collaboration is essential for advancing chip technology. Scientists and engineers from around the world are sharing knowledge and resources to accelerate progress. Joint projects and conferences foster innovation and help solve global challenges. This scene highlights the importance of working together to shape the future of computing. Next-generation chips will impact consumers in many ways. Faster devices, smarter assistants, and more secure systems are just the beginning. As photonics, quantum, and neuromorphic chips become mainstream, everyday technology will become more powerful and efficient. This scene explores how these advances will benefit users and change daily life. Shift beyond silicon is creating new business opportunities. Startups and established companies are developing innovative products and services based on photonics, quantum, and neuromorphic chips. These technologies are opening up new markets and driving economic growth. This scene discusses how businesses can capitalize on the next wave of computing. Advanced chip technologies bring new security challenges. Quantum computers could break current encryption, while neuromorphic chips may enable more sophisticated cyber attacks. Researchers are developing new security protocols to protect data and systems. This scene examines the risks and solutions in the era of next-generation chips. As we look to the future, the possibilities of computing beyond silicon are endless. Photonics, quantum chips, and neuromorphic computing will continue to evolve, unlocking new capabilities and transforming industries. The journey is just beginning, and the next decade will bring exciting breakthroughs. This scene encourages us to stay curious and embrace the changes ahead. Summary: the era beyond silicon is opening up new horizons for computing. Photonics, quantum chips, and neuromorphic computing are not just theoretical concepts, they are real technologies shaping our future. As we continue to innovate and collaborate, these advances will lead to smarter, faster, and more efficient systems. The vision for tomorrow's computing is bright, and the journey beyond silicon is well underway.